Section 7.3, we learn about oblique triangle trigonometry. So we notice that we've got three kinds of triangles that we're going to be concerned with. We have the right triangles that we talked about, where we have one right angle and two acute angles. So this is a right triangle, one right angle, two acute angles, we can have an acute triangle, acute triangle has three acute angles and an obtuse triangle has one obtuse angle and two acute angles. And recall, an acute angle has measure greater than 0, less than 90, and an obtuse angle has measure greater than 90, less than 180. Turns out if you get to 180, then, well, it's technically obtuse. But at that point we would call it a straight angle. And at that point it's not a triangle anymore. So actually we should actually make it less than 180. We notice that at 0 degrees or 180 degrees, it is no longer a triangle. We notice that for 0 degrees, we would just get a line segment. A, B, and C would match. And if we had 180 degrees, we notice again, not a triangle. So it turns out that we have this phrase in a big triangle is just a triangle for which none of the angles is 90 degrees. And it turns out that we have an interesting quirk of triangles that lets us still find out things about these. So we have something called the law of sines. The law of sines lets us know that in any triangle in any triangle capital A, B, C, the ratio of sine A to the side opposite A is equal to the ratio of sine B to the side opposite B and sine C and the ratio of sine C to the side opposite C. So notationally, we're saying that sine of A divided by lowercase a has to equal sine of capital B divided by lowercase b has to equal sine of C divided by lowercase c. And so it turns out if we drew a triangle with angle measure 30 and 4 and 7, we could figure out the other two angles. So we'll just call this A equals 30. And we'll have angles B and C. Actually, we can't do that just yet. We actually would have to have it arranged like this. So if we had A is 30 and lowercase a is 7, we can figure out what B and C have to be. We notice that we can say sine of 30 divided by 7 has to equal sine of C divided by 4. And that also has to equal sine of B divided by lowercase b. So how can we do that? We notice that we can find out that sine of 30 is 1/2. So we know 1/2 divided by 7 equals sine C divided by 4. That means that we get 1/14 equals sine C divided by 4. And we can multiply both sides by 4. Sine C is going to equal 4/14, or we could say that's going to be approximately equal to 4/14 is approximately 0.286, approximately 0.286, and so now we can use that inverse sine idea. We can say C should be approximately equal to the inverse sine of 0.286, which is going to give us 16.6 degrees. And so once we got that 16.6 degrees, we now know that we had 30 and we got 16.6. We know 30 degrees plus 16.6 degrees plus b has to equal 180 degrees, because some of the angles has to have 180, and so b has to be approximately, so this will be approximate because the 16.6 was approximate. We know that b has to be approximately 180 minus 46.6, and so that gives us 133.4. And so now we can go back and say that that sine of 30 divided by 7 has to be the sine of b, 133.4, divided by a lowercase b, and so we can find out that we'd already seen that that was going to be 1/14 equals the sine of 133.4 divided by b, so we know b equals 14 times the sine of 133.4, and then we find out that the sine of 133.4 is approximately 0.73, so that would be approximately 14 times 0.73, which is going to be times 14, we get around 10.2. You notice that we can't use Pythagorean theorem anymore because it's not a right triangle. That said, we do notice that law of sines does work on right triangles, it just winds up being not nearly as interesting. So we notice that if we're going to look at something like one of our classics, if we look at 6, 8, 10, do we go down? No, that one gets messy. We don't do that one. If we do 6, 12, 6 radical 3, that turns out to be a triangle that is 30 degrees by 60 degrees by 90 degrees. We might or might not talk about that a little bit more. But what we notice is that if we look at law of sines, we know that sine of 30 divided by 6 should equal sine of 60 divided by 6 radical 3, and sine of 90, that should equal, both of those should equal sine of 90 divided by 12, and we can verify, we notice that we're going to get sine of 30 divided by 6 is going to be 1/2 divided by 6 equals 1/12. We notice that sine of 60 is radical 3 divided by 2 divided by 6 radical 3 is going to be 1/12, and sine of 90, if you tried it on your calculator, you would get 1 divided by 12, which is 1/12. And so we notice that for a right triangle it's boring, but it's nice to know that it still works. So you notice that works well if we have an angle and a side opposite that angle. So we notice that given A and A, we can solve the triangle with lowercase, well, basically with any two other angles and sides. We can either have lowercase b and lowercase c, the angle b and the angle c, or some mix and match of that. We could have lowercase b with capital C, or capital B with lowercase c. So you could either have both other sides, both other angles, or an angle on the side. Other sides, other angles, or a mix. So the trouble is, what if we're not given lowercase a and capital A? We have another trick we can use called the law of cosines. So the law of cosines is a bit fussier. The law of cosines lets us know that for any triangle, with angles A, B, C, and side A, lowercase a opposite capital A, lowercase b opposite the angle B, lowercase c opposite angle C, we know that a squared, lowercase a squared, has to equal lowercase b squared plus lowercase c squared minus 2bc lowercase b, lowercase c cosine of capital A. And similarly, b squared equals a squared plus c squared minus 2ac cosine of capital B, and c squared has to equal a squared plus b squared minus 2ab cosine of c. And so it turns out this law of cosines actually ends up being a more general case for Pythagorean theorem. You notice that this third one, if capital C equals 90 degrees, cosine of 90, you can find out that the cosine of 90 is equal to 0. We just get c squared equals a squared plus b squared. So what winds up happening is that if we're given a triangle and we knew that we had two sides, say side 4, side 8, and we knew that that angle between them was, let's make it 60 just to make life convenient, we notice that we can find A, we can decide that this 4 is equal to B, 8 is equal to C. We can say that A squared is equal to 4 squared plus 8 squared minus 2 times 4 times 8 times the cosine of 60. And so we're going to get 16 plus 64 minus, that's going to be 64 times 1/2, because cosine of 60 is 1/2. So a squared is going to be 16 plus 64 is 80 minus 32. A squared is equal to 48. And so A is going to be square root of 48, which turns out to be square root of 16 times 3. Sorry, square root of 16 times square root of 3. And so we end up getting 4 out of 3. And so we notice if the angles are nice, it'll turn out to be fairly convenient. The angles will not often turn out to be nice. So we could then find out the other two angles we wanted to would turn out to be we could find out, so we notice that we could use law of sines. We could say sine, so let's see, we said lowercase b was 4, so capital B is going to be opposite side 4, and capital C will be opposite side of length 8. So we now know that if we take sine of 60 divided by 4 equals 3, that has to equal sine of capital C divided by 8, and that has to equal the sine of B, capital B, divided by 4. And so we notice that sine of 60 is radical 3 divided by 2, so we're going to turn out to get 1/8 equals sine C divided by 8, and so that means 1 equals sine C, and so that means that C has to be 90 degrees. And we notice that we'll get 1/8 equals sine B divided by 4, and so sine B equals 1/2, and so B turns out to be 30 degrees. And so, like I said, that one winds up being not terribly interesting, because it turns out to be a 30, 60, 90 triangle. But if we had something a little more exotic, if we tried saying something like, let's make this 6 and 4, and we'll make this angle 40 degrees. Now, this is very much a calculator question. We can't easily do this by hand. We notice that we could again say this is side lowercase a. We can decide that this is angle capital B, this is angle capital C. And we again notice that a squared is going to be 6 squared plus 4 squared minus 2 times 4 times 6 cosine of 40. And so we're going to get 36 plus 16 minus 48 cosine of 40. And now we get into a lot of calculator work again. We're going to get the cosine of 40 is approximately equal to 0.77. So we're going to get 52 minus 48 times, so we'll say approximately 52 minus 48 times 0.77. Remember, we can't subtract until we first take 48 times 0.77. So we'll get approximately 36.8. So let's call that. So this is all a lot of approximation. So 52 minus 36.8 gives us 15.2. Double check that. We're going to get 46, 51, yep, 15.2. And so we know that A is going to be approximately equal to the square root of 15.2, which is approximately, if we take 15.2 and take its square root, we're going to get approximately 3.9. And now we notice that we can find out the measured angle B. We know that sine of 40 divided by 3.9 has to match up to the sine of capital B divided by 4, and that has to be the sine of capital C divided by 6. And so we notice that we find out that sine of B, we said sine of 40, actually we have to figure out what sine of 40 is. We know sine of B is going to equal 4 sine 40 divided by 3.9. Sine of C equals 6 sine 40 divided by, where'd it go? 3.9. And so from there, I'll leave that as an exercise. We notice we're just going to get some value for sine 40 multiplied by 4 divided by 3.9, and then we can use inverse sine. So B will be the inverse sine of 4 sine 40 divided by 3.9, and capital C will equal inverse sine of 6 sine 40 divided by 3.9.